Last week we talked about current mirrors, and there was one very good question. Thought it would be better if I answer that question to all of you. So I will go through some current mirrors, random process variations, and then systematic errors in the current mirrors. This is again, some talking about good analog design practices, which you have to keep them in mind. And after that, we will start on a different topic, which is differential amplifier. Rest of this week, we will be focused on differential amplifier. First, we will look at the current mirror, revisit current mirror, simple current mirror. We already went through this equation. I out divided by I ref is equal to W by L of transistor 2 divided by W by L of transistor 1, and then 1 plus lambda effect, which is in this case it's V out divided by 1 plus lambda, lambda 2 and lambda 1, and this is VGS. A couple of things I talked about last time and it wasn't very clear, so I'll go through that again. The first thing is going to be about random process variation. When we draw these transistors in silicon, we use techniques such as lithography. You already know about that, and let's kind of draw the picture about how it really looks like. So if let's say this is your, this is the diffusion region, and it will have some jittery edges, and let's say this is our poly. I'm intentionally making it not look very good, and this is the drain, and let's say this is a source. Okay, so this is supposed to be our channel length L, and this is supposed to be our width of the channel W. Okay, so these are the edges which define the transistor. They look like over here, right? There is one edge. These are the two edges which will define the width, and these are the edges which will define your length, the distance between them. The thing is, because of lithography, there is noise on these edges due to the random variation, due to the wavelength of the light that's being used. I'm going to borrow some of the statistics concepts. I'm not going to go dive deep into it, but I'm assuming that you know the basics. So sigma is, let's say, the standard deviation, and then sigma square is your variance. So in this particular case, the current I, okay, is proportional to W by L. Now each W and L are going to have some variation, right? So in this particular case, we can say that sigma I divided by I square is equal to is proportional to rather than equal to, we can say that is sigma W divided by W square plus sigma L by L square. Basically, each one of them are independent variables, and W and L are independent. That's what we're assuming. So we have RMS addition between these two statistical quantities, right? So the assumption here is W and L are independent variables. Okay, so now in this particular case, you can quickly see that if W is, let's say, much greater than L, which can be many times that's the case, because you're trying to get large currents and or gain, then typically W is much larger than L in analog design. So then you can quickly see that sigma I by I square is kind of proportional to sigma L by L square, because the L mismatch will random variation in L will pretty much dominate the entire behavior of sigma I by I square. Okay, now the question is, hey, if you take one transistor, okay, so the question was as follows. Let's say I have one transistor with certain W by L, okay, and if I stretch that transistor, and let's say here this is say some value, okay, and this is, let's say, 10W, this is 10W, and this is L, right? If I do it this way versus if I do 10 units of the transistor, something like this, Right now I'm showing only 3, but you can imagine there are 10 units like that, and each one of them is W by L. What I suggested last time was, hey, this would be preferred because you would have exact same statistical behavior on your W's and L's. You may be able to get very similar result over here because finally you can chop this transistor in like this to make 10 units, and then statistically you probably can get pretty much similar behavior. However, if you take into effect the length variation, channel length variation, then my hunch or my intuition tells me that the W by having 10 units rather than one single unit with 10 W is definitely better, because now, first of all, I can one of the important things in when you do the layout is the following. You don't really lay out. Let's say there is one transistor called transistor A, and then let's say I have transistor B, which is let's say in this particular example, let's say just there are 4 transistors. 4 units of 4, right? So this is B. Then you really don't lay them out next to each other like this, because what will happen is, these guys are on one side, this guy is on one side. The statistical variation and also, the slope of the oxide, those would be very different. And sometimes A could be a lot bigger than unit size of B. So what you do is you do something called common centroid layout. In this particular class, we are not going to do any layout, but it's good to understand what's really going on. So when you lay this transistor out, it's better to lay it out this way, which is, let's say this is A. Then one way would be to draw this B on one side, and then you would draw the other B's on this side. So then you would get pretty good matching, because the common centroid of B transistors and A transistor is the same. And even better layout would be if you do this, if you do one A transistor here, and then you would do the other transistors over here. So this would be your B, and B, and B, so that it's right in the middle, the transistor A, which is from which you are multiplying. So analog design is all about this. Basically, how do you make exact copies in presence of all manufacturing variations? So this is what we talked about, is all random variation. Now you can also have what I'm going to talk about is something called systematic errors. Okay, so systematic errors. When it comes to systematic errors, you can have layout related errors, and I'm going to explain all of them. And then you can have design errors. So this is like operator error, I like to call them. So errors. So layout errors could be the different orientation. You don't lay it out properly. The transistor A is laid out horizontally, transistor B is laid out vertically, and W is perpendicular to each other between the two, then they will obviously not match. Okay, so different orientation, this could be a problem. And when it comes to design, for example, if you have different VDS between the transistors, then you will not get exact same matching. When it comes to systematic errors, you can say that basically each defining edge or dimension, can have errors. So for example, if you look at a transistor, okay, so you have this is your sandwich, this is your oxide, and then here is your source and drain regions, right? So you can have errors in your channel length, you can have errors in your channel width, also you can have errors in your TOX, thickness of the oxide, and all these will give you different behavior from one transistor to another. So let's take a couple of examples for your understanding, and then it will be clear why I'm telling you about making unit cells rather than having transistors by just stretching their widths. You should always use a unit cell, and then you stamp that unit cell multiple times, and you lay it out in such a way that you get the best matching between the two quantities, two transistors. Okay, so let's take an example of channel length. If you look at the transistor in a classic sense, right? This is the way it looks like. If the cross section looks like this is your oxide, and this is your gate. The hashed portion is your gate. Okay, and then if you remember when we studied the transistor action, right? Let's say this is your N plus. What we said is, this part is our drawn channel length, L drawn. What does L drawn mean? Let's say I choose channel length when I'm drawing the transistor in your in the Cadence or any other software. When you're doing the design, going through the design process, let's say you choose it to be 1 micron, 2 microns, and things like that. So that would be what you would control when you're drawing the rectangle. Okay. However, we already know that because of the diffusion will travel laterally, okay, on both sides, and then you will end up having this error. You will have lateral diffusion of LD, okay, in this case. So then your L effective is actually L drawn minus 2 times LD. So now you can pretty much get hang of it. If I simply stretch the transistor when it comes to increasing the channel length, right, then you can immediately tell that, hey, if let's say I would like to have a transistor with n times L drawn. Okay, let's say I want n times L drawn. In that particular case, the L effective is going to be equal to n times L drawn minus, again, it's going to be 2 times LD, because this happens only at the end when you come to source and drain region. So this doesn't get multiplied. So you can quickly tell that if you just take a transistor and stretch its length, then you really don't get this exact multiplier of n. When you want to do scaling by factor of n, then you should take the transistor and you would repeat it multiple times and then connect them in a series fashion, so your channel length is increased exactly n times. Okay. Generally, you don't do that about the channel length. You would rather focus on the channel width. But here is just an example. Just to show you why not to do it. Let's look at channel width, transistor channel width. Okay, so width W. So let's go through the MOS cross section again, and then you would have some metal contacts right here for source and drain regions. Right now they are not coming to the play, but I'm just showing you visually how it's going to look like. Okay, and now let's say we take a cross section right here where the green line is. That's where I take a cross section. When you physically make this device, this is the way it's going to look like. You will see something like this. So this would be your oxide, and this would be your let's say substrate, and this would be, let's say, somewhere here you would have your channel. Okay, and then the poly would look actually like this, which is kind of interesting, and I just wanted to show you why that happens. This is our poly, which is the gate, the one which is in magenta. This is your poly gate. So you will say that, hey, why does this happen? So we have something called field oxide, which is over here, okay, which is separating the, we call it FOX, field oxide, and it gives you an effect which kind of looks like a bird's beak over here. When you need a desired W, let's say you have W drawn, is what you want, you actually get W plus delta W. Okay, so this plus delta W is something that happens because of these two edges which are defining your width, right? Now what happens is if I just stretch the transistor simply to increase my W, then this this W will get multiplied, but this delta W will not get multiplied. So for example, let's say I have two transistors. Let's say if I have M1, which is W by L, and let's say M2, which is 2W. Let's use a generic number. Let's say M2 is N times W divided by L. So what I have done is I have taken a transistor W by L, and then I stretch the W to make it N times larger, N being some, let's say, integer for the sake of this discussion. Now what will happen is if you look at the current mirroring between these two, what you would get is you would get I out divided by I ref, Okay, that would look like, so for example, the NW plus delta W you will see, and then L plus delta L you will get, and then reciprocal of that will be L plus delta L divided by W plus delta W. So this happens because the delta W doesn't get multiplied in this case because we are stretching the width. So you will still have the same variation for a single unit W or n times larger width. All right, so and you can immediately see now we are going to get it's NW plus delta W divided by W plus delta W. So this would be the scaling that you're going to get, and obviously you can tell that it's not exactly N that we decide. Okay. Now, however, if I would have a transistor M1 which is a W by L unit and transistor M2 which is W by L, and then I would make it, I would have multiplier of, let's say, N, which means I'm stamping this transistor of W by L N times. N is the integer. Then what will happen is your I out divided by I ref, that will be equal to, you will get NW plus N times delta W. I think this should be pretty obvious. L plus delta L multiplied by L plus delta L divided by W plus delta W. Here you can quickly see that I will get N W plus delta W divided by W plus delta W. So I should get the exact factor N. And what I'm trying to tell you is that these two factors, the random variation as well as systematic errors, you will have to take into account. And in both cases, you benefit by having unit cell structure for the transistor. Now, you don't do this only for transistor, you do it for many other things. For example, you would use the resistors also in the same way, or you would do the capacitors the same way. So when it comes to resistance, for example, when you draw the resistor, right? So for example, I have this resistor, and then at the end, I'm going to put some contact, right? Like this here. Generally, you have multiple contacts. Now, I can, let's say I need 2 times this resistor exactly. Then you could technically say that, hey, why don't I just increase the resistor? Let's say this is width W, then I'll do 2W, and at the edges I will put this put these contacts. Now these two will not match because you will have this edge effect over here, which is not scaled. Okay, so a better solution would be to have 2 units of the resistors which look exactly the same way, so that any kind of contact resistance or edge effects, they also get multiplied. I think you get the hang of it. What I'm trying to do here, even when it comes to capacitors, the same rule applies. When it comes to capacitor, what you're looking for is actually absolute value of the capacitance you can get between the 2 plates, right? Now you would like to make sure that you stamp the same unit capacitor multiple times, so you get the same behavior, because each capacitor will have some parasitic capacitance, and that parasitic capacitance also you would like to have it scaled. Instead of just scaling the area of the capacitor, if you like really exact capacitive scaling, let's say you want ratio of 10 between C2 and C1, then you don't just increase the area of C2 by 10. What you do is you make one capacitor C1, and then you stamp that capacitor 10 times more to get your 10 times C1. So this particular philosophy, you use it for every component that you would be laying out on the chip. And these are very specific when it comes to chip. Because you're drawing all these devices on the chip and you would like them to match very well. When it comes to components, there you cannot really control each and every individual component that you're getting it from the lab. So now we will start with the next topic, which is going to be a differential amplifier. So why do we need differential amplifiers? So let me give you an example of a ECG or medical related. Before even that, when you were working in the lab, many of you must have touched the oscilloscope probes. And what do you see when that happens? If you observe the screen carefully, you will see, like specifically if the oscilloscope is somewhere in the 10 millivolts per unit scale, then you will see a really large waveform going up and down on the scope. And if you hold the probe in your hand, then you'll probably see some kind of 50 hertz hum on the screen. When you're trying to measure ECG, for that matter, right, you're connecting, let's say in this particular case, let's say you're connecting two probes to your body, and you're looking for difference in the voltage between these two probes. So the difference between the two probes is a very small value. It could be in microvolts type of range, and the common mode signal which you see when you touch the oscilloscope probe can be very high. It could be in millivolts value. So so what are we really looking for is we would like to look at a very small differential signal. For example, the difference between the voltage measured between the two probes in presence of a very large common mode signal. For example, common mode means the same signal is there on both the probes, for example. Okay, so let's say there is a terminal P and terminal N. What you would really like is the between the two terminals, P and N, the difference between those two we would like to amplify by a large value. However, anything that exists on terminal P and N together, common to both those terminals, VP and VN, like a large hum, that we would like to subtract it out. So as a concept, we call single-ended signal, signified like this. This is your plus minus, and this is your VSE, and its VSC is equal to VC cos omega CT plus VD cos omega dt. Again, this is just to make you understand what this means. So VC could be the large undesired signal, for example, undesired signal, and this could be in millivolts range, let's say. And VD is the differential, or rather than you can say it's a desired small desired signal, and let's say it's in microvolts range. So what we want to do is we want to get rid of this, but we don't want to we want to amplify this as a differential signal, DE, differential signal. We show it like this. So you have two outputs. One of them is like the VDE plus, which you can say it's VC cos omega CT plus VD cos omega dt, and then on the other side I'm going to show again VDE minus, which would be VC cos omega CT minus VD cos omega dt. Now you can pretty much tell that when I look at voltage between VDE plus and VDE minus, then VC cos omega CT would be like a common term and it should get subtracted out, but then VD cos omega dt, here on one side is positive, the other side is negative. So when you look at the difference between the two, that would go through. When we draw the picture of this, for example, let's look at two different frequencies. So in this case, let's say I have this is my VC, right? And then on top of that, I'm going to draw my VD signal. So let's say here it is going like this, okay, and here it is exactly opposite. So if we delete the green part, then you can kind of say that, hey, the magenta curve is the sum total of these two, okay, right here, and this is over here, and the green part is your the common mode signal. So common mode signal shows up the same way on both sides, but the differential signal shows in opposite phase on both sides. Okay, we have and this common mode could be due to a variety of reasons. It could be due to supply hum, 50 hertz noise coupling, or variety of different types of noise couplings on chip. Name it. So our goal is to only amplify the desired signal and reject the common mode signal. The simplest thing that we have learned so far, and let's see how that behaves, is, let's say I would take a, I think you should be able to tell what the circuit is. What is this circuit? You should try to answer in your head what kind of configuration it is. This is a common source or common emitter. It should be common emitter amplifier, okay, CE amplifier. So now here we have VDE plus going in here and VDE minus going in here. This is your resistor R and this is your VCC. What will happen is this common emitter amplifier will offer large gain to VDE plus and VDE minus. Okay, so here we have a waveform that looks like this, something like this, and here you have another waveform that looks like this. And when you amplify it, what you would see is at this output, okay, on one side you will see a flipped waveform which would look like this, and here also you would see something like this. Okay, now if the gain is too high, then what you would also you could get into a situation where the waveform gets clipped, which means you will see something like this, something like this. So this is not a good situation, and the other side will also look the same way. I'm going to just draw it here, so you get the something like this. Okay, and we are supposed to look at the difference between the two waveforms. So you can say that this common mode signal, the large common mode signal, is actually overdriving this stage, and it's clipping the output because the amplifier does not have ability to distinguish between undesired and desired signal, common mode signal and differential signal, right? So it would amplify both the signals, and it would since the common mode signal is large, it will also amplify that, and it will drive the amplifier into clip. This definitely, circuit is not exactly, I mean, it behaves differentially. We have differential input and differential output. However, the common mode part is not rejected. The common part, which is on VDE plus as well as VDE minus, that is not rejected. It will amplify both of them, and it will get in trouble. So this particular topology is called pseudo differential. So our goal again is to amplify only the differential signal and reject the common mode signal. So here is the innovation that is real fundamental to circuit design, and it's used almost everywhere. So let me draw it for you so that it will be clear. So it's a basic differential pair circuit, and it looks like this. So I'm going to just draw the bipolar case first. Just a small modification compared to what we did before, but that modification makes a world of difference. RC, okay, and this is our Q1, and here what we have is a current source, okay, and I'll just call this as 2I, saying that each side is carrying the current I, bias current, okay. So now in this particular case, when we apply this signal which has both common mode as well as differential, something like this, what you would see is the following. The common mode signal which is there on Q1 and Q2, what ends up happening is, since the current here is limited to 2I, it doesn't really show up at the output, and we are going to go through why that happens, okay. And what you would see at the output would be something that would look like this, something like this, and then you would see opposite phase signal. So when you look at the differential signal, you will get a really large desired signal being amplified, something like that, okay. So that would be the time scale is not correct, but I think you get the point. So this would be since, let's see, this is your VI plus, this is VI minus, so then you would get an inversion here. This would be VO plus and this would be VO minus. All right, this current source which we introduce is affectionately also called as a tail current source, and all of us know by now how to implement these current sources. That's what we learned in the previous lecture. What you see here is the common mode signal will move both the bases up and down, and along with that you would see this the tail current source node also move up and down with the same waveform. However, that will not change since this is a constant current source. It will not change any current flowing through the output load resistors RC, as a result of which you will see that the common mode signal is rejected and only the differential signal is magnified. Let's go through a little more details, detailed qualitative analysis of the diff pair. So I'll be drawing this many times, and so should you. Okay, and this is our 2I current source, and this node is called, let's say, V tail. Okay, and I'm going to label them in a certain way so that our analysis becomes easy. VIP, VIN, and this is your load resistor RC, and VCC, and this would be exactly flipped so that you would call this VOP, and this is VON. When you apply a apply voltage VP and VN, okay, on each side, let's say you apply that voltage, then you pretty much know, we can figure out what the VCM is. VCM will be VP plus VN divided by 2, okay, and VDM, which is differential signal, that would be VIP and VIN. Okay, this is VIP and VIN input. So this would be VIP minus VIN divided by 2. No, not divided by 2. This should be just the same. Okay, so that would be our differential mode signal. So then from this equations, we can rewrite VIP is equal to VCM plus VDM, which is differential signal, divided by 2, and VIN is equal to VCM minus VDM divided by 2. What we have done is the two input voltages VIP and VIN we have constructed with common mode part and differential mode part. So remember, the common mode part should have the same signature, same sign on both sides, whereas the differential part will have a positive and negative sign, and that's why it's called differential signal. So now from this we can kind of start analyzing the circuit, right? So for example, we can use our superposition ideas, and let's first only apply VCM to our circuit. Okay, so then we can draw the picture again. 2I, and this is so let's say I'm only applying VCM to both sides. What do we see when we apply VCM? I want you to think about it for you can pause the video and think about what will happen if I would apply VCM. So pause the video, think about it, and come back, and then you can listen to it again. Okay. So when you apply only VCM, which is the common mode signal to both sides, right? Then what will happen is since the VBE on both sides will be equal, right? Because the V-tail node is common for both of them, and base voltage is also common for both of them. So then the current should split equally on both sides, right? So the Q1 and Q2 both will carry current I. Both will carry current I through this resistor, okay? And then our VOP, which is here, output, and VON, which is over here. So what we expect is VOP is equal to VON, that would be equal to VCC minus I times RC, okay? So convince yourself of this one, and here you can quickly tell that this answer is independent of VCM. And that's the beauty of it. Okay, and whereas V tail, if you look at the tail voltage, what would that be equal to? V tail voltage will be equal to VCM, which is the base voltage, minus you will have VBE for both the devices, right? And they should be same. So VCM minus VBE, that should be the tail voltage. So now what we are going to do is on top of this VCM, I'm going to apply the voltage VDM, okay? And then we will see what happens. So for example, let's use this. Let's draw the circuit. Okay. So now we will apply VDM. Again, this VDM is a differential signal. So on one side we will apply VDM by 2. Other side we will apply VDM divided by 2. Okay. So we had the circuit looks like this. I'm intentionally focusing on this circuit quite a lot because it's very important to understand this very well, because this is like the foundation circuit which you will be using in many places. Okay, so we have in this particular case we would have VCM, and on top of that I'm going to apply VDM divided by 2, and here I'm going to apply VDM divided by 2 minus VDM. Then what will happen is, let me add other information, RC, VCC, okay, and this is your VON and VOP. As we said again, the VTEL should pretty much remain the same, which is VCM minus VBE, average VBE, okay. Now this is due to the common mode part, when the current supported is I equally. All right, so when I apply VDM, then what do you expect? Then you would expect, you're expecting this voltage to go up, this voltage to go down on the because I'm applying positive voltage. So then the what you expect is that the current through this transistor will increase, and that would be equal to GM times VDM divided by 2, and the current through this transistor will be minus GM times VDM divided by 2. Okay, so that would be the differential component. So then after applying VDM on top of VCM, what we see is we see VOP, which was originally VCC minus IRC. Okay, that was the original value without VDM, and on top of that you would see plus sign GM VDM divided by 2. That would be the current due to the transconductance of the transistor. This is Q2 and this is Q1. Okay, and multiply that current by RC. Okay, and similarly VON, that would look like VCC minus IRC minus GM VDM divided by 2 RC. Okay, so now we can look at the, finally what matters is the differential voltage that will be going to the next stage. So what we are looking for is VOP minus VON. That's the voltage that you're looking at, and you can quickly see that this is going to look like GM times VDM times RC. The differential output differential voltage, which is V out differential divided by V in differential, that would look like VOP minus VON divided by VDM, and that would be equal to GM times RC. So note, in this particular case, the GM that we are talking about is the transconductance of each transistor, and that is when it's carrying current I. Okay, common mode current I. Also, one more thing I would like to bring it to your attention is when the left side goes up and right side goes down, right? The tail current node, the tail current source voltage across the tail current source, that doesn't change. Because the differential voltage that you're applying is absorbed in the VBE of Q1 and is removed from the VBE of Q2 by this value, and what you would then see is the tail current node V tail will always remain fixed. In this particular case, VBE is the VBE when you are carrying constant current I. Okay, not with the differential current going in. As you can see, since the tail current is only carrying constant current 2I, and the voltage across the tail current source doesn't change, you can say that, hey, this particular node, the V tail node, is a virtual ground. There is no current going no matter what the input is, no differential current is going in that node, as well as the voltage is not changing. So it looks like a ground node, right? So for the differential signal point of view, this looks like a virtual ground node. We will stop right here, and then we will start again in the next lecture.